Welcome to this rigorous scientific lecture on the fascinating physics and chemistry of egg white foam. Today we'll explore why egg whites whip into stable foam and, more importantly, why even a tiny amount of fat causes catastrophic collapse. Let's start with a fundamental question. What is egg white foam? At its core, it's a colloidal dispersion of gas bubbles in a liquid protein matrix. We have air bubbles surrounded by thin films of protein. The protein molecules arrange themselves at the air-water interface, stabilizing the bubbles against collapse. Before we understand foaming, we need to know what's in egg white. The composition is critical to the mechanism. Egg white is approximately 90% water by mass and 10% protein. The remaining fraction includes trace minerals and glucose. The protein fraction consists primarily of ovalbumin at 54%, conalbumin at 13%, and ovomucoid at 11%. These are globular proteins. Globular proteins are folded into compact, three-dimensional structures. They have hydrophobic cores and hydrophilic exteriors, making them soluble in water. Let's examine what happens to these proteins at the molecular level during whipping. Native proteins are compact and folded. When we apply mechanical work through whipping, we denature them. The proteins unfold, exposing hydrophobic amino acid residues that were buried in the core. The mechanical energy input from whipping breaks hydrogen bonds, van der Waals interactions, and disrupts hydrophobic interactions. These are non-covalent bonds with energies around 4 to 20 kilojoules per mole. Let's pause and ask, how much energy does whipping actually provide to denature proteins? Can we estimate this? Let's do a back-of-the-envelope calculation. Assume we whip for 5 minutes at a typical mixer speed. A typical electric mixer operates at about 100 watts of mechanical power. Whipping for 5 minutes means 300 seconds of operation. Energy equals power times time. 100 watts times 300 seconds gives us 30,000 joules, or 30 kilojoules. A typical egg white has a mass of about 30 grams, or 0.03 kilograms. This gives us about 1,000 joules per gram of egg white. This is substantial energy input, more than enough to denature proteins. Now let's examine what happens at the air-water interface. This is where foam stabilization occurs. Water has high surface tension, approximately 72 millinewtons per meter at room temperature. This creates an energetic cost for creating new surface area. When we introduce air bubbles by whipping, we create vast amounts of new air-water interface. Denatured proteins adsorb to this interface because they can lower the surface tension. Denatured proteins are amphipathic. They have both hydrophobic and hydrophilic regions. The hydrophobic parts orient toward air, hydrophilic parts toward water. Pure water has a surface tension of 72 millinewtons per meter. With protein film, the surface tension drops to approximately 50 millinewtons per meter. This reduction of 22 millinewtons per meter is energetically favorable. Here's an important question. When we whip egg whites into foam, how much surface area do we actually create? Let's calculate. Egg white foam can expand to 6 to 8 times its original volume. Let's assume 7 times expansion. Starting with 30 milliliters of egg white, the foam volume is 7 times 30, which equals 210 milliliters. The air volume incorporated is 180 milliliters. Let's assume the average bubble diameter is 100 micrometers, or 0.1 millimeters. The radius is 50 micrometers, or 5 times 10 to the negative 5 meters. The volume of one bubble is 4/3 pi r cubed, which equals 5.2, 4 times 10 to the negative 13 cubic meters. The number of bubbles is the total air volume divided by single bubble volume. This gives us 3.4 times 10 to the 8th bubbles, or 340 million bubbles. The surface area of one bubble is 4 pi r squared, which equals 3.14 times 10 to the negative 8 square meters. The total surface area is the number of bubbles times the area per bubble. This gives us 10.7 square meters of interface. That's enormous. From just 30 milliliters of egg white, we create over 10 square meters of air-water interface. This represents a massive increase in surface area that must be stabilized by proteins. Now let's understand exactly how the protein film stabilizes bubbles against collapse. There are 3 key mechanisms by which protein films stabilize foam. Let's examine each one. First, proteins reduce surface tension. Lower surface tension means lower Laplace pressure driving bubble coalescence. The Laplace pressure is given by 2 gamma over r, where gamma is surface tension and r is bubble radius. By reducing gamma from 72 to 50 millinewtons per meter, proteins reduce the Laplace pressure by about 30%. Second, proteins form a viscoelastic film. The adsorbed proteins interact with each other through hydrogen bonds and disulfide bridges if oxidation occurs. This creates a cross-link network at the bubble surface. The film has mechanical strength and elasticity, resisting deformation and rupture. Third, proteins provide electrostatic repulsion. Proteins carry net charge, typically negative at pH values above their isoelectric point. Egg white has a pH of approximately 9, which is alkaline. Ovalbumin has an isoelectric point around 4.5. At pH 9, which is well above the isoelectric point, proteins carry a net negative charge. This causes electrostatic repulsion between adjacent bubbles. Even with protein stabilization, foam is not perfectly stable. Let's discuss foam drainage. Gravity causes the liquid phase to drain downward through the foam structure. This is called syneresis or foam drainage. As liquid drains, the films between bubbles become thinner. Eventually, they may become unstable and rupture. The drainage rate depends on the viscosity of the liquid phase and the bubble size distribution. Smaller bubbles drain more slowly. Now we arrive at the central question. Why does even a tiny amount of fat cause catastrophic foam collapse? This is fascinating physics. Fat molecules, particularly lipids and triglycerides, are extremely surface active. They adsorb to air-water interfaces much more readily than proteins. When a fat droplet contacts the protein film, it spreads rapidly across the interface. Fat molecules displace proteins because they lower surface tension even more. Let's compare surface tension values to understand the thermodynamic driving force. Pure water, 72 millinewtons per meter. Protein-covered interface, 50 millinewtons per meter. Lipid-covered interface, 25 millinewtons per meter. Fat lowers surface tension by a factor of 3 compared to pure water and by a factor of 2 compared to protein films. The tendency of fat to spread is quantified by the spreading coefficient. This tells us whether spreading is thermodynamically favorable. The spreading coefficient S equals gamma protein minus gamma lipid minus gamma protein lipid interface. The protein-lipid interfacial tension is approximately 5 millinewtons per meter. Therefore, S equals 50 minus 25 minus 5, which equals 20 millinewtons per meter. A positive spreading coefficient means fat will spontaneously spread across the protein film. The process is thermodynamically favorable. Let's examine the detailed mechanism of how fat causes foam collapse. This happens in stages. Stage 1. A fat droplet contacts the thin protein film between 2 bubbles. Here are 2 adjacent bubbles with a protein film between them. A small fat droplet makes contact. Stage 2. The fat spreads rapidly across the film surface, displacing protein molecules. The protein film is now replaced by a lipid film. But lipid films lack the mechanical strength of protein films. Stage 3. The lipid film cannot resist drainage forces. It thins rapidly and ruptures. The film ruptures. The bubbles coalesce into one larger bubble. Stage 4. This creates a cascade. As bubbles coalesce, the foam structure collapses progressively throughout the entire system. Here's a critical question. Exactly how much fat is needed to destroy foam? Can we estimate this quantitatively? Let's calculate based on molecular areas. We need to know how many molecules are required to cover the interface. A single lipid molecule occupies about 70 square angstroms, or 7 times 10 to the negative 19 square meters. Recall we calculated 10.7 square meters of total interface in our foam. The number of lipid molecules needed to cover the interface is 10.7 divided by 7 times 10 to the negative 19, which equals 1.5 times 10 to the 19 molecules. Converting to moles using Avogadro's number, we get 2.5 times 10 to the negative 5 moles. assuming an average lipid molecular weight of 800 grams per mole. The mass needed is 0.02 grams, or 20 milligrams. Just 20 milligrams of fat, which is about the mass of one small drop, is theoretically sufficient to destroy the entire foam. This is why fat contamination is so problematic. But the situation is even worse. Fat doesn't need to uniformly coat the interface. Even a single point of contact can initiate spreading that propagates throughout the foam. Now let's discuss the kinetics. Why does foam collapse so rapidly once fat is introduced? We can estimate the spreading velocity using the meringue effect. This is flow driven by surface tension gradients. The velocity scales as delta gamma over eta, where delta gamma is the surface tension difference and eta is the viscosity. The surface tension difference is 25 millinewtons per meter. Water viscosity is 1 millipascal second. This gives a characteristic velocity of about 25 meters per second. This is extremely fast. Given bubble diameters of 100 micrometers, fat can spread across an entire bubble in microseconds. This explains the rapid collapse. An interesting question: can we use emulsifiers to prevent fat-induced collapse? What does food science tell us? Emulsifiers, such as lecithin, are amphiphilic molecules that can stabilize both protein foams and fat droplets. Lecithin molecules have a hydrophilic head group and hydrophobic tails. They orient at interfaces with intermediate surface tension. Lecithin-covered interfaces have surface tension around 35 millinewtons per meter, intermediate between protein and pure lipid. However, lecithin doesn't form the strong viscoelastic films that proteins do. It reduces the spreading coefficient, but doesn't eliminate the problem. Let's briefly discuss temperature effects. Temperature significantly affects both protein denaturation and foam stability. Cold egg whites, around 4 degrees Celsius, whip to smaller volumes but produce more stable foam. The proteins denature more slowly. Room temperature egg whites whip to larger volumes more quickly. Proteins denature more readily, but the foam may be less stable. Temperature affects both the viscosity of the liquid phase and the kinetics of protein unfolding and adsorption. What are the practical implications of this science for cooking? Let's translate theory to practice. First, ensure all equipment is absolutely clean. Even trace amounts of fat from previous use can destroy foam. Second, separate eggs carefully. Egg yolk contains approximately 33% fat by weight. Even a tiny speck will cause problems. Third, use copper or glass bowls rather than plastic. Plastic can retain fat residues that are difficult to remove. Fourth, adding acid, such as cream of tartar, lowers the pH slightly, which can enhance protein-protein interactions and foam stability. Fifth, if making meringue, add sugar gradually after soft peaks form. Sugar increases viscosity and helps stabilize the foam structure. Let's examine the physics of bubble coalescence in more detail. This is governed by film drainage dynamics. Film drainage between two approaching bubbles is described by the Reynolds drainage equation. The rate of film thinning, dH by dt, equals negative 2 h cubed p over 3 eta r squared, where h is film thickness, p is pressure, eta is viscosity, and r is radius. Notice the cubic dependence on thickness. As films get thinner, drainage accelerates rapidly. Films typically rupture when thickness reaches about 100 nanometers. Below this, van der Waals forces overcome stabilizing forces. An advanced concept relevant to foam stability is disjoining pressure. This is the pressure that acts to separate two interfaces. Disjoining pressure has three components: van der Waals, electrostatic, and steric contributions. Van der Waals forces between bubbles are attractive, promoting coalescence. These dominate at short range below 10 nanometers. Electrostatic repulsion from charged proteins opposes coalescence. This is the origin of the electrostatic stabilization we discussed earlier. An interesting question: why do egg white foams become brittle and less stable over time? What's the molecular basis? Over time, proteins in the foam undergo further cross-linking through disulfide bond formation. This requires oxidation. Excessive cross-linking makes the protein film more rigid but less flexible. It can't accommodate deformation without cracking. Additionally, water evaporates from the foam, increasing protein concentration in the films. This leads to gelation and brittleness. This is why dried meringues are crispy and brittle rather than flexible foam. The protein network has become a rigid, glass-like structure. Let's make an illuminating comparison between soap bubbles and protein foam. Both are stabilized foams, but with different mechanisms. Soap bubbles are stabilized by surfactant monolayers. Soap molecules are small and mobile, forming dynamic films. Protein foams are stabilized by cross-linked protein networks. These are much more rigid and less dynamic. Soap bubbles pop instantly when the film ruptures. Protein foams can tolerate small ruptures because the network structure provides mechanical integrity. However, both types of foam fail catastrophically when fat is introduced. For the same reason, fat displaces the stabilizing molecules. Let me now summarize everything we've learned into a complete physical picture. Step 1. Mechanical work from whipping denatures globular proteins, exposing hydrophobic residues. Step 2. Denatured proteins adsorb to the vast air-water interface created by bubble formation, driven by reduction in surface free energy. Step 3. Adsorbed proteins interact to form a viscoelastic network that resists deformation and drainage. Step 4. Charged proteins provide electrostatic repulsion that keeps bubbles separated. Collapse mechanism. When fat contacts the foam, it spreads rapidly due to favorable thermodynamics, displacing proteins and eliminating the stabilizing network. Result: without mechanical support, films rupture and bubbles coalesce in a catastrophic cascade throughout the foam. This phenomenon is part of the broader field of colloid science, which studies dispersed systems. Foams, emulsions, and suspensions are all examples of colloidal systems. They share common stabilization mechanisms. Understanding protein foam stabilization helps us understand emulsion stability, suspension stability, and other colloidal phenomena. These principles have applications far beyond cooking, including pharmaceutical formulations, foam materials, and industrial processes. In conclusion, the simple act of whipping egg whites involves sophisticated physics and chemistry. We've explored protein denaturation, interfacial phenomena, surface thermodynamics, and colloidal stability. We've seen quantitatively why even tiny amounts of fat destroy foam, through fundamental physical principles of spreading and displacement. This demonstrates that rigorous scientific analysis can explain everyday culinary phenomena. The kitchen is a laboratory for exploring fundamental science. Thank you for joining me in this detailed scientific exploration of egg white foam. The interplay of proteins, interfaces, and lipids creates a rich system worthy of rigorous study.